Multiclass logistic regression. Multiclass logistic regression, also called as multinomial logistic regression or softmax regression. This is an extension of logistic regression that handles multi-class classification. So 2 lectures back, we learned about logistic regression, and there we did two-class classification or binary classification. Here we are going to do k-class classification or multi-class classification. This is the only difference. When we wanted to do binary classification, we use something called as sigmoid function. And here, in order to do k-class classification, we'll be using softmax function. So the main difference between binary logistic regression and multi-class logistic regression is that in case of binary classification or two-class classification, we use the sigmoid function, while in multi-class classification, we'll be using softmax function. So this is the major difference. Let us see what exactly are the differences as we go through this lecture. First thing, our input format. Let us say our input is x, and x can be written as something like x1, x2, x3 up to, let us say, xn. So this is an n-dimensional input. And in this input, let us say you can classify into one of k different classes. This is the problem statement. How do you do this? First thing is about softmax function. In the previous lecture, we learned about softmax function. So it was something like this. Softmax of I is equal to e power ai divided by sum over all the classes. That is, let's say j is equal to 1 to k e power aj. Okay. That is, in the denominator, you are summing over all the possible classes, and in numerator, you take the exponent only of the corresponding class for which you are taking the softmax. So here, ith class is what you are taking the softmax for. So in this case, here you know what A is, right? A is your W1, W0 plus W1x plus, let's say like this, W0 plus W1x1 plus W2x2 plus dot 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 up to Wnxn. So this is what your A is. So we'll write this in a short form, as instead of writing this, we'll write it something like W transpose X plus W0. And instead of W0, we can write it as B. So B is bias. So W0 term, we'll call it as B. Okay. So this is the scenario. So let us start with the problem. Let us understand how to solve this. So if it is for, let's say for the kth class, how do you find the probability for one particular class? Let us say I want to see the probability that this particular point belongs to the kth class. So for that, I'll do something like this. Probability of y is equal to k given x. That is, x is your input. Given the input x, what is the probability that this particular input belongs to the kth class? In logistic regression, using the softmax function, how do you write this? This can be written as e power your W transpose X for the kth class. So kth class, you have wk transpose X plus bk divided by sum over all the classes. How do you do sum over all the classes? J is equal to 1 to k e power wj transpose X plus bj. Okay. So this is how you find probability for the kth class using logistic regression. The same way, you have to find the probability for each of the class, and whichever has the highest probability, that is the class to which you will assign this. Okay. So just keep this in mind. So as we do the derivation, when we use the softmax function, I'll simply denote this as sk. So when I denote like sk, you should understand it is this particular function. Or when I say si, see, this is the format of the function that you have to, formula of the function that you have to keep in mind. So going forward, when I simply write sk, si something, so you should understand this is the equation that I mean. Okay. So this is the softmax function. And what are these terms? Let me just explain you so that there is no confusion hereafter. What are each of the terms here? The term WK that is used here. What is the WK? WK, it is the weight vector that is corresponding to the kth class. And what is BK? BK, this term, BK is the bias corresponding to the kth class, BK, or you can call W0 also. So I'm not using W0 because then you will have to write W0K, which will be tougher to understand. So I'm writing it as BK. That is why I choose B instead of W0. Then the other terms are Bj and Wj. So Wj is the weight vector corresponding to jth class. Bj is the weight vector corresponding to jth class. So this is the terminology that you have to understand here. So let us get into this. Let us understand how it works. Okay. So exact details of the softmax function we already discussed in the last lecture. There is a special lecture on softmax, so you can refer to that if you want complete details of how the softmax works and what it is. Okay. So let us start with this. So in the training, how do you train this? You want to find the optimal weights, that is WK and BK, the biases and the weights for each of the class. You have to find the optimal weight for which, for the class K, it will maximize the likelihood of observed data. So this is what we do in all the machine learning problems. You want to find WK and BK, that is the coefficients which will maximize the likelihood. This is what you always want to do. So how do you do this? By taking the maximum likelihood estimation as always. So first let us understand maximum likelihood estimation like we did in previous logistic regression, and let us solve with it. Okay. So the likelihood in this case, the likelihood of the point belonging to one particular class. Let us understand that likelihood. And what are the coefficients you have? You have W and B. Okay. Likelihood corresponding to W and B. So using this likelihood, we'll try to optimize and find the optimal W. Okay. So while considering the likelihood, what is the probability for one particular point? Let us say you have m different input points, input data that is, and let us say each of this data can belong to one among the k classes. Okay. There are k classes and each of the m different input can be of any of the k classes. So in total, you have m different inputs and each of those input can belong to any of the k classes. This is the problem scenario. Okay. So in that case, how can you write the total likelihood? First thing, you have m different input. So you know the probability for one particular input belonging to one class is probability of y is equal to k given x. Okay, we already saw this. What if you have k different classes and m different inputs? Then for each of the class, you have to see this probability, and that you have to do for all the m inputs. How do you find that probability? Because it is probability, you have to multiply. So for m different classes, multiply, that is pi. Let us say I is equal to 1 to m, that is over all the m different inputs. Next thing you have to consider k classes. So pi, let us say k is equal to 1 to k. So over all the k classes. Then what is the probability? Probability of yi, that is the ith input belonging to kth class, right? Yi is equal to k given xi. And one more thing is, here you took the probability of yi, that is the ith input belonging to kth class given xi. Xi is the ith input. Here, one thing you have to notice, you have to put this delta ki. What is this delta ki? This delta ki, this will be the value 1 if this ith training example belongs to kth class. And if this ith training example, this does not belong to kth class, then it will be 0. Why should it be 0? Because if it does not belong to kth class, then for that particular point, this term is invalid. So you want to make this 0. So this is 0 means it will be, this term will become 1. If you take the exponent of 0, it will become 1. And if it becomes 1, when you multiply, it will become invalid, right? Invalid in the sense that particular term won't be counted. So this is delta ki, that is ith training example belonging to the kth class. If it belongs, its value will be 1. If it does not belong, its value will be 0. Okay. So till now it is clear, right? So now you have likelihood. The next step is, like we did in the case of a previous logistic regression class, we'll take log likelihood. Why are we taking log? Because this will make a computation easier. So log likelihood is LWB is equal to, what is log? You have to take the log of this whole thing. Okay. So in order to find the log likelihood, I'll take log of this whole thing. So how can this be written? When you take log, multiplication will turn to addition. So this will become, instead of a multiplication, it will be summation. Sigma I is equal to 1 to m, and this term will again become summation. So it will be sigma k is equal to 1 to k. Then I have to take log, right? Log of p of yi is equal to k given xi whole raised to delta ki, right? So I'm going to rub this off. This is my log likelihood. So if I simplify this further, log of a raised to b can be written as b log a. That is, if you have something like log a power b, this is same as b into log a. So using this equation, this formula of log, you can rewrite this as sigma I is equal to 1 to m, sigma k is equal to 1 to k. This will become, this delta will come to the before the log. Okay. So this will be delta ki log of p yi is equal to k given xi. Okay. This is xi. So this is your log likelihood. So what is the next step? You want to maximize log likelihood. That is when you will find the optimal W. Okay. So before we maximize log likelihood, this calculation that we have done, this is for all the training examples. That is, we counted all the m different training examples. But let us take one training example and do the calculation, because that will make a calculation easier. So we'll remove this I equal to 1 to m summation, and we'll take the log likelihood for one particular training example. So let us denote it by Li of WB. So here I'm considering only one particular training example. So this term will stay and this summation will remove, because I'm not going to consider all the m. So I don't have to sum over all the terms. I'll take just one term among those sum. So it will become sigma, and instead of this k, I'm going to convert it to j now. J is equal to 1 to k. This term will remain as it is. So it will be delta ji log of probability of yi is equal to, instead of writing this yi equal to all these things, let me simply write it as sigmoid function. You'll understand, right? So I'll simply write this as sigmoid function sji. Okay, it is the sigmoid function. So this thing, this probability, it is the sigmoid function. So if I write this whole thing throughout the solution, I'll have to write the whole. So it's easier to notate it as softmax. Sorry, not sigmoid. Here it is softmax. In the binary logistic regression, we used sigmoid. Here we are using softmax. Okay. So it is sji. So let's continue with this. So here I have the log likelihood corresponding to one particular training example. So for one input, this is my log likelihood. What is the next step? I have to maximize the log likelihood. I have to find the value of W and B, which will maximize this log likelihood. So How do you maximize? You have to find the derivative with respect to W. So for each of the W's, you have to do this. We'll do for one W here, okay? So let us say for kth class, I'll consider Wk. So in order to consider Wk, I'll take derivative with respect to Wk. So it will be del by del Wk of this term, right? Log likelihood of Wb. What will this be? If I take the derivative with respect to Wk, this will become sigma j is equal to 1 to k del ji into this term. I have to again take derivative with respect to Wk. So it will be del by del Wk of Sji, right? Sji. So this is what I have to this is how I have to maximize. I have to take the derivative and find the optimal value of W possible. So in order to take this derivative, let us solve this part by part. First I'll solve this particular part and then we'll combine everything together. So in the sigmoid lecture, we already learned how to take the derivative of a sigmoid function. What did we learn? We learned something like this. In order to take derivative, del by del Wk of the softmax function. Sorry, it's not sigmoid, it's the softmax function here. Both are similar. The thing is, softmax function applies for multi-class classification and sigmoid for binary. Okay. So here I am taking that of sigmoid, let us say of Sji. If I take the derivative, what will it become? It will become Sji into del jk minus ski into, then inside the sigmoid I have the xi term, so that I'll take outside here into xi. So now the derivative of sigmoid, I'm just taking the derivative of this part. So if you remember in this sigmoid lecture itself or the softmax lecture itself, we had explained what is the derivative of softmax. So here I'm directly using that derivative of softmax. For exact derivation of softmax, you can refer to the softmax lecture. Okay, here I'm directly using the derivative of the softmax function. So how can you understand this function? Here this del term, del jk, this term will take the value 1 if it belongs to that class, that is both j and k are one and the same, and it will take the value 0 in case j is not equal to k. So in case j is equal to k, if j is equal to k, what will this become? This will become Sji into 1 minus, because this term will become 1 minus ski into xi. Okay, this is what it will become. So here remember, this is the case when j is equal to k. So Sji and Ski will be one and the same. So in this case, Sji into 1 minus Ski into xi. This is what you get. What if j is not equal to k? If j is not equal to k, in that case, what you get is minus of Sji into Ski into xi. How's this? Because this will become 0. So this minus, this I took outside. Okay. So Sji would be the, Ski would be the, and into xi. Okay. So the derivative of softmax, if j is equal to k, then this will be the derivative of softmax, and if j is not equal to k, then this will be the derivative of softmax. So softmax has two derivatives depending on the value of j and k, whether j is equal to k or not. So the same thing is depicted by this function. I just simplified so that you understand how this delta works here, delta jk. Okay. So now I'll erase this off. We'll use delta only in our derivation. Okay. So the next thing is, we need to find the derivative in case of log. So there is one mistake here. I have log Sji. So this has to be in log. Okay. So this should be del by del wk of this term. Okay, so log has to be there, so it will be log sji. Okay, right, now it is fine into xi. So now what you have to do is you have to find the derivative of this term del by del wk of log sji. So here you know the derivative of sji. The next thing is you want to understand the derivative of log of this. Okay, so let me try to get that here. What you have to get is del by del wk del by del wk of log of sji. Okay, this is what you want, log of sji. If you take this derivative, what happens? Log x derivative is 1 by x, so it will become 1 by sji into the derivative of sji, and the derivative of sji you already know, this is del by del wk of sji. So that is this term, del by del wk of sji. So this I can substitute here. The only difference is this 1 by sji term which came here because of the log. So now if you take the derivative of this whole thing, what will you get? This thing into, so I'll do this here only. This is this term, that is del by del wk of sji, this into 1 by sji. Okay, this 1 by sji. So what will happen? This sji and this sji cancels out. So what remains? What remains is del jk minus ski into xi. So I'm going to write it here. Here this will become delta jk minus sji. So here I'm writing this ski into xi. Okay, so now you have del jk minus ski into xi. So this is your del by del wk of log sji. So you got this term. This term you know now. So the next thing is you have to find the derivative of the whole, that is del by del wk of li. Li is the log likelihood. So this wb I'm not writing, I'm directly writing li. Okay, so this is the derivative of the log likelihood. So in the log likelihood, what you have to see here is this term I told you, it will be 0 if it belongs to this particular class, and 1 if it will be 0 if it does not belong to that class, and 1 if it belongs to the ith class, jth class. That is, here you are going through all the classes. You have ith training example with you. If this ith training example belong to the kth class, jth class, then del ji will be 1. If it does not belong, then del ji will be 0, which means when you sum over all the values of k, only one value will be 1. All the other cases will be 0, because this training example can belong to only one particular class among all the k. Because of that, when you sum over, only one value will be 1 and all the remaining will be 0. Okay, so I again need not sum over all the values, because I already know that only one will be 1 and all the remaining are going to be 0. So only one particular value is significant. So when I write this, I can write this as, here I got the term xi into delta, here I have taken k and I, so it will be ki minus ski. Okay, so this will be my log likelihood function. Okay, the derivative of the log likelihood function. What I wanted to do, I want to take the log likelihood function, I want to maximize it and find the optimal values of w's and b's. In order to do that, I took the derivative of this log likelihood function, and that is what I got here. I have to take the derivative with respect to each of the coefficients wk. So here I am taking with respect to a coefficient wk. Understood? So the next step, I'll erase all these things. So the next step, what I got now is over one particular training example. That is, we had limited our calculation to one particular training example, the ith example. For the ith example, I found the derivative of log likelihood. Next step is I'll expand this to all the training examples back. So how can I expand this back to all the training examples? Del by del wk of L. So I'm not taking Li, log likelihood, for all the training examples. So what do I have to do? I have to sum over all the m different training examples. So it will be sigma I is equal to 1 to m. That is, I'm summing over all the training examples. Then it will be xi into delta ki minus ski. So this is the log likelihood, derivative of the log likelihood for all the training examples, because initially I found for one particular training example, that is one input data. I know there are m different input data and we have to consider all input data and then see the log likelihood and maximize it. So here I'm considering all the training examples here by summing over all the m values. Okay. So till this point, why did I take this term out? Because this summation term is not going to make any changes in our derivative calculations. But if I had the summation term, in every step I would have had to write this. So which would make the whole mathematics look more complex. So just in order to avoid that, I avoided this. I went to one particular training example, I took the derivative. Once I reached the final answer, I inserted the summation back. Okay, there is no other complexity here. Just to avoid writing this in every step, I avoided that at that time. I took for one particular training example, and once I reached my final answer, final solution, I included the summation and took it for all the training examples. Okay. So now you know the derivative of log likelihood. What is the next step? And one more thing I'll tell you, we already did it for WK. So following the same procedure if you do for BK as well. B is the bias term, that is instead of W0 that would have been W0K. So we used BK. So if you do the same steps for BK, this is what you get, del by del BK of L. If you do for each of the I examples, what would you have done? Del by del BK of log of Sji. This is what you would have done. And if you do this, you would have reached delta Jk minus sigma softmax of Ki. This is what you would have reached. So again, if you take for all the I examples, del by del bk of L, this if you would have taken, what would you have got? You would have simply taken summation I equal to 1 to m. You would have taken this xi term, this won't be that. That's the only difference that's going to happen with this. It will be delta ki minus ski. So the same term you will get as this wk. The only difference is this xi term, this won't be present in case of the bias term. Why it won't be present? Because if you see the equation that we started with, it was something like this: w0 plus w1 x1 plus w2 x2 plus up to wn xn. Okay, so all the w terms had an x term with it, but this w0 term, this is what we denoted by b, this b. So because of that, W0 does not have a bias, does not have an x term attached. So for the bias, when you take derivative, there won't be x term. The remaining whole procedure is the same. Okay, you can just say the same procedure and try doing on yourself. This is the final answer you're going to get. I just wanted to write the final answer here. Okay. So this will be del by del bk of L. That is, if you take for the bias term, it will be sigma I is equal to 1 to m. This xi won't be there. It will be delta ki minus ski. Okay. So these are the two derivatives that you want. One with respect to wk and one with respect to the bias term bk. What is the final step? The final thing is, in logistic regression, like we did in case of binary logistic regression, we want to find by gradient descent method, you have to find the exact or optimal values of W's. So how will you find WK? Each step, we discussed in logistic regression lecture that in each step you will update the values of W. You will initially have some initial value, let's say for WK, each of the WK you will put some initial value, maybe 0 or a very small value, a finite small value. The same you will do for BK. You will either initialize BK with 0 or a very small value. Then in each step, you will update the value of WK. The 0 will be updated in each step, and as you reach an optimal solution, that is when you stop. So the stopping condition we'll again discuss. WK, how do you update in each step? Okay. WK, the updation of WK, that's what we are discussing. WK will be updated as previously existing WK minus eta into del by del WK of L. But there is a small catch here. If you had listened in a logistic regression lecture, that is binary logistic regression lecture, we had told that we took negative of log likelihood instead of log likelihood. So we had used this formula along with negative of log likelihood. In this particular case, we used log likelihood, we didn't take the negative. So see, you can solve either ways. The only difference is when you are taking negative of log likelihood, this equation stands. This negative came from the negative of log likelihood. But here, because you are not taking negative, you will directly put plus here. Both works. So in case of previous logistic regression lecture, you would have seen that we used minus here and not plus. Why did we use minus? Because we used minus here, and then here we used negative of log likelihood. Here we are using not negative, we are taking the actual log likelihood and we maximized it. Previously what we did, we took negative of log likelihood and minimized. Okay, we took the negative of log likelihood and we minimized it. Here we took positive itself, the log likelihood, and maximized. So here instead of negative, plus would hold. Okay, I just wanted to explain why I am writing plus here, because I used minus in previous lecture. So I don't want you to be confused. There it was negative because we used negative log likelihood here. So that minus and this minus would cancel off. Okay. So here it is positive. So this is the updation formula for WK, and the same goes for BK. How would you update BK? BK will be updated as BK plus eta into del by del BK of log likelihood. Okay, and this del by del BK and del by del WK you have here. So this term you have from here, this term you have from here. Okay, so this is how you update the values of W and B. The next thing is, as you go on updating, when do you decide to stop? So one stopping condition is when you update this WK, let me call this WK dash. If WK and WK dash are almost same, that is the difference between them is very small, then you would decide that okay, I reached a threshold, I don't want to continue further, I consider it as the optimal value of W. So if the difference between this WK dash and W is very small, that is it is negligible, then you would say yes, I reached a final solution, this is my optimal W. That is one way. The other way is, one other way is, if this gradient, that is del by del WK of L, this derivative of log likelihood, if this term is very close to 0, if it is almost 0, then there is no major update that is going to happen. So in that case also you would say okay, I have reached the optimal W, I am going to stop. And the other way is, you would fix some particular number as the maximum number of iterations you want to do. Let us say you fixed 1000 as the maximum number of iterations you want to do. So if you do this updation 1000 times, then you would automatically say okay, this is my optimal W, I'll stop. So these are the methods by which you generally decide that you reached an optimal value of W. So we've discussed everything. Okay, one thing is, what is this eta? Eta is the learning rate. If you put a high value of eta, each time it will take a big leap. That is this del by del WK, that is your gradient. That will be multiplied with eta, which is your learning rate. If learning rate is very high, each time WK will be updated by a large margin. If this eta is very small, then each time your WK will be updated by a small margin. How to choose this? That is depending on your particular case. You have to choose it by looking at the case you are solving. Sometimes slightly larger value is better, sometimes a smaller value is better. So you have to get the right balance of the eta value. It will help you reach the optimal solution faster. Okay, so this is logistic regression. You update the values of WK, you update the values of BK, then you find the optimal value of W and B. Once you find that, what will you do? You will use the softmax function. We already discussed softmax function. If you know W's and B's, you can directly apply it in the softmax function where we had e power, let's say WK transpose plus BK divided by sum over all the values. That's what we had done. So if you know W and B, then you can directly use in softmax function. I'll just write it down here so that there is no more confusion on how this works. Softmax function, we had it as e power for the, let's say you're checking for the kth class. Then you had WK transpose X plus BK divided by sum over all the classes j equal to 1 to k e power Wj transpose X plus Bj. So here, if you look at this, if you know all the W's, WK, BK, Wj, Bj, you'll get all the W's by optimizing and finding the optimal value. If you know all the values, then you can directly substitute those values here, and the only input is X. If you know X, you know WK, you know BK, you know Wj, Bj, X as well. So if you know all these, you can find the value of softmax, and whichever class has the highest softmax value, that is the class to which you want to assign this input value. So this is how you do multi-class classification using softmax function, that is logistic regression.